Hello, everyone. My name is Nick Rychek, and this is our Project 3 presentation for ESC 220. The title of our project is the Cold Work Hardening of Aluminum and Steel Daggers. In this project, I modeled what happens when you take two common engineering materials, aluminum and steel, and reshape them into dagger-like rods by cold working. I'll be walking through how the deformation process affects their tensile strength, ductility, and microstructure. And I'll back everything up with real experimental data that we collected in lab. The goal here isn't just to compare which metal is stronger, but to understand why one hardens differently from the other. The main objective of this project was to apply our tensile and hardness data to a real-world situation, forging a dagger shape. We started with aluminum and steel rods of 5 centimeters in diameter and reduced them to 3 centimeters. This reduction simulates a heavy cold working process. I wanted to compare how this affects their mechanical properties, especially tensile strength and ductility, and then explain it through the lens of material science, dislocations, grain structure, strain hardening. So this project connects what we did in the lab directly to industrial metalworking.
Hi, I'm Ozone. So for slide 3, both materials started as 5 centimeter diameter rods, and our target final diameter was 3 centimeters. The reduction in area is a really important value to calculate because it tells us how much plastic deformation the material experiences. Using the formula, R equals A initial minus A final, all divided by A initial multiplied by 100, with area equals pi times d squared divided by 4. We get a reduction of about 87%. That's a huge amount of deformation, which means we're introducing a lot of dislocations and internal strain energy into the structure. At this point, even before testing, we expect both materials to get stronger and less ductile because of that high amount of cold work. Here's the data we gathered from the tensile test. For aluminum, the original gauge length was 59.5 millimeters, and the broken length was 56.5 millimeters, so elongated by about 3 millimeters, which gives us roughly 5% ductility. For steel, the unbroken side was 42.8 millimeters, and the broken side was 81.4 millimeters, giving a much larger elongation, around 90%. Now that 90% might sound a bit high, but what it really shows is how much more stretch steel can handle for fracture compared to aluminum. This tells us early on that steel has a much higher capacity for plastic deformation. It can absorb a lot more energy for breaking.
Hi, my name is Tristan Allen and I'll be talking about steel dagger properties. For the steel dagger, the goal is to have a ductility higher than 15% and a tensile strength above 800 megapascals. With the 87% reduction in cross-section, our steel reached an estimated tensile strength of around 850 to 900 megapascals, which meets and even exceeds that goal. However, as expected, the ductility dropped, likely down to around 12 to 15%. This happens because cold working introduces more dislocations in the metal lattice. These dislocations start to tangle and block each other's motion, which makes plastic deformation more difficult. So the steel becomes much stronger, but also less flexible. A classic example of the strength ductility trade-off. If we apply the same 87% reduction process to aluminum, the story is a bit different. Aluminum's starting tensile strength was around 200 megapascals. After cold working, it could rise to roughly 320 or 350 megapascals. So it does not get stronger, but the ductility drops drastically from about 30% before working to maybe 5 to 7%. This shows that aluminum can't store as many dislocations before the material fails. Its crystal structure allows easier slip, but that also means it hardens faster and becomes brittle more quickly. So while it strengthens, it loses most of its ability to deform without breaking. Not ideal for a dagger or any tool that needs toughness.
So I'll be talking about the effect of cold work on a stress strain curve. This graph shows how the stress strain curve changes after cold working. The yield point and ultimate tensile strength both increase, meaning the material resists deformation much more. But the curve shortens. Ductility goes down because the metal can't stretch as much before fracture. In simple terms, we made the metal stronger, but we also made it more brittle. And that's the balance engineers always deal with, finding the sweet spot between strength and ductility for a given application. Now let's talk about what's happening at the microscopic level. During plastic deformation, dislocations multiply inside the crystal lattice. As more dislocations form, they start to interact and look each other in place. This is called dislocation entanglement. Grains also elongate in the direction of deformation. This gives the metal an anisotropic structure, which is why cold work metals often show direction-dependent properties. Aluminum, which has a FCC structure, has many slip systems, so dislocations move more freely. That makes it easier to deform, but it also means it reaches its hardening limit faster. Steel, on the other hand, especially carbon steel, with both BCC and FCC phases, has stronger interactions between dislocations and can sustain higher work hardening before it fails.
So, here's a clear comparison between the two materials. Aluminum started around 200 megapascals and ended around 320 megapascals, while steel started closer to 600 and ended around 850 megapascals. Ductility in aluminum went from 30% down to 5%, whereas in steel, it dropped from 25% to around 15%. What this tells us is that both materials got stronger and less ductile, but steel kept a better balance. Its final ductility is still acceptable for something like a blade, while aluminum isn't. This is one of the key takeaways. Different crystal structures respond differently to the same level of cold. Now, connecting this to our hardness data. The increase in hardness after cold work directly correlates to tensile strength. There's an empirical relationship that says the ultimate tensile strength is roughly 3.45 times the brittle hardness. When we tested the steel after deformation, its hardness increased significantly, which aligns perfectly with the increase in strength we saw. Aluminum's hardness also increased, but to a smaller degree, again showing its lower hardening capacity. This consistency between tensile and hardness data validates our results and proves that our mechanical testing was reliable.
So what do these results mean in practical terms? If we were actually forging daggers, the steel version would be far more functional. It's strong, tough, and can hold an edge. Aluminum, though lightweight and corrosion resistant, simply doesn't have the mechanical strength or toughness needed for a blade. It would bend or dull too easily. However, aluminum could still be used decoratively for training daggers, cosplay, or lightweight models. This shows how understanding cold work and mechanical properties helps us choose the right material for the right job. To wrap everything up, cold working increases strength by introducing dislocations, but it always reduces ductility. Steel responds to cold working with a large gain in strength while still keeping reasonable ductility, which makes it ideal for structural and tool applications. Aluminum also strengthens but becomes much less ductile and can't handle as much further deformation. So, from both a mechanical and microstructural point of view, steel is clearly the better choice for something like a dagger, where hardness and edge retention are crucial. This project helped us connect our tensile and hardness lab data to actual manufacturing processes like forging and metal forming.